Соответственно, семинары у нас проходят на английском, но если у вас возникают вопросы, то вы можете спрашивать их на русском, или голосом, или в чате. Соответственно, что еще? Если будут проблемы со звуком, то тоже говорите. So today we consider PyTorch library. Well, a long time ago, when deep neural networks has just proved to be effective, there was no straightforward way to write your own neural network. I mean, to write neural network which is trained on GPU, you have to write C++ code with CUDA kernels and so on. But, well, because neural networks were necessary for a lot of machine learning tasks, the machine learning libraries that helps to write neural networks appear. Such libraries are Caffe, Ciano, TensorFlow, PyTorch, Keras probably. The main common thing about these libraries is that they firstly allow you to do computations on GPU without writing a lot of low-level code. And second part, they have out-of-the-box automatic backpropagation. The thing you heard about in the previous lecture, I think. So I just pasted the link to our today's notebook in the chat. So you have to download it. Well, now the question, this size of notebook is okay, or you need a bigger font?
It's okay, yeah.
Oh, thank you. Okay, now another question. Did you use NumPy? Do you know NumPy?
Yes, of course.
Okay, perfect. So so it will be much easier to understand a torch. Well, actually, from one side, the first part, you can think of PyTorch as of NumPy with GPU support. So in NumPy, you can create tensor, reshape it, and do some basic mathematical operations with it, such as addition, multiplication, matrix multiplication, averaging, and so on. And actually, you can do the same things in PyTorch. Uh, well, first of all, you can create uh, torch tensor from NumPy tensor uh, in a couple of different ways. Uh, you well, as in NumPy, you can change the type of your tensor, or you can create a torch tensor using just torch library. Uh, and with this tensor, you can do the same operations as in NumPy. But the yeah, naming on the of the functions and function arguments in PyTorch is slightly different from NumPy. So instead of dot, you have matmul. Instead of x along which you average your tensor, in PyTorch you have mm, dim for dimension. But in general, the interface is almost the same. Uh, okay, and you can not only import NumPy tensor into PyTorch, you can export PyTorch tensor back into NumPy. Right. Oh, well, actually, in PyTorch there are a lot of different functions, so uh, naturally I will not cover all of them here. So if there is something implemented in NumPy, for example, uh, you can try to find this the same thing for PyTorch in the docs or using Google Stack Overflow and so on. Okay, here we have a simple example how we uh, perform mathematical operations over mm, torch tensors. So here we make array with numbers from 0 to t, and then we just check that well, let's say Pythagore theorem in holds in PyTorch. But now we see it doesn't hold exactly because we have some floating point operations residuals. Uh, so one thing which is different in NumPy and PyTorch are so-called in-place operations. Well, in-place operations is operations which doesn't create a new object uh, which contains the result of the operation, but modify the input object instead. So mm, why do you need in-place operations? Usually the case is when you need to uh, when you have a limited amount of memory and you need to well use it carefully. Uh, so The naming convention is that the mathematical operation with which ends with underscore in PyTorch is in place operation, and the operation without underscore is not in place operation. So the default, well, the default behavior for PyTorch is not in place operation, which is more or less natural for neural network. How to say, for for neural network purposes. So in this example, we see that we have an array, and not in place operation doesn't change the original array, and in place operation returns changes the original array and returns its changed version. Uh, and here is the example where it might be useful. If you write, if we have say three matrices and we do such, we want to calculate such an expression, we probably need three memory locations to get the intermediate tensor results. But we can do the same thing using just one tensor location and then applying in-place operations. So we first take y, then we multiply it by 2, then we in place add and subtract other two matrices, and this one is takes less memory and is probably faster because of that. But using this is not a common thing. Any questions so far? Okay. Now broadcasting. Do you know how broadcasting in NumPy works? Oh, great. Okay, so here we have the once again quite similar behavior. The point is that if we have say two two arrays with different shapes. For example, I don't know. Let's make a different size of this arrays, and we want to obtain the matrix where the yj's element is the sum of a of the first matrix i's element and the second matrix j's element. So if you want to get d yj equal to a y a0 plus b 0j, we can use broadcasting. So if the if one dimensionality is the same dimensionality in one tensor is equals to one, and in other not equals to one, then the behavior of broadcasting is similar to uh, that we expand the first tensor over this dimension to match the dimensionality of the second tensor, and then perform the operation. That's the thing. So that is how it works. We take 1 0 1 0 1 0 and add 1 1 1 2 in different rows to it, and we obtain such a matrix. Uh, and if you have any questions, you can read the docs once again. And here we have our first problem. The problem is follows. Oh, the question. Uh, well, no, for mm, uh, mm, well, okay, a lot of in-place operation that does not support backpropagation through them, so you just get some error when you call the backpropagation over the computation graph with in-place operation, but some operations which are invertible support in place backpropagation. So, for example, if you have leaky relay, you can do it in place. There is a flag to do it in place, and then you can backpropagate through such in place operation. So there are some exceptions. Okay, the problem now is that we have a set of objects and a set of what we call them control points. All these points live in 10-dimensional space. So the objects are in metric X, and the control points in the are in the matrix Y. Sorry. The goal is to find for each object the index of the nearest control point and probably the distance to it. And naturally, well, just everybody can write nested loop for this problem, but we want to vectorize it using torch operations in order to make it fast. So if the statement is clear, I just give you some time to make solution.
Добрый день. Прям судьба сегодня нам второй урок просидеть. Я правильно поняла, что мы должны просто найти, типа, наименьшее расстояние, ну, типа, два элемента из x и y, между которыми наименьшее расстояние? О, Господи. Тоже сделала, я так понимаю, да? Тут что, просто циклом пройтись или я что-то не знаю? Все. Ага, и что? Я просто не знаю операции с тензором, если честно. Вот это мы проблема. Я говорю, у меня единственная идея была вот с циклами. Больше у меня вообще никакого алгоритма в голове. Ладно, сейчас что-нибудь попробую сделать.
Okay. Does somebody have a solution?
Yes. Should I say it or write in chat or how
You
do you
can
want?
write into the chat. The question was, does everybody have a solution?
Like, should I write it or not? I just don't understand.
Yes, yes. You can paste into the chat. Okay, and why is that?
Because matrix multiplication will do the how's it called? The will find. Yes, it's incorrect. Yes, that's absolutely bad idea because it's not. It's just scalar products, not the actual distance.
Okay, maybe other solutions. Okay, mm, let's get to it. So the first solution is uh, very straightforward. What do we need? We need to compute the first of all, we need to compute the matrix of distances between uh, each object and control point. So we can do it using broadcasting. We like reshape the first matrix into this shape, uh, and we subtract the reshaped matrix of points. So now is J's cos element of this tensor is the difference between the same dimension of one object and one control point. So we naturally compute the well square it and sum over the last dimension and take square root. So now we have the matrix of Euclidean distance between each 2 points. And well, here it is. And to obtain the indices of minimal of the proposed point to each object, we would use argmin in NumPy, but in Torch we use just min. This function returns a tuple, the first element of which is the, well, okay, let us rewrite it to make it more clear. This is the distance matrix, and now we take minimum over the which dimension? Over the last dimension, and the result, the tuple with the first element is minimum, and the second element is the argmin. So here is the vector of minimal distances, and here is the vector of IDs which we need. No, this tuple is not named. We just oh, okay, yes, it's named, but I can see why it's important. Well, okay, this one would be more nice. I agree. Now, the drawback of this solution is that we have very, very large intermediate tensor, of shape number of objects times number of points times the dimensionality. While actually we need only number of objects times number of points. Memory to store our distance matrix, and it is not clear why we have to use additional memory to compute it. And actually, the point is because we want the element of our distance matrix to be x y minus y j. Squared and the sum of this over k, we can use scalar product. We can say that distance between y and j's y's object and j's point equals to x squared minus well, surely we have some here, but we can just open well, the square, and we have x squared plus y g squared minus 2 times x and yj's. And now we see that this one is just matrix, well, just a scalar product between the object and the point. And actually, matrix multiplication just gives us this the matrix of such scalar products. But while the original solution was incorrect, we had not such additions to this scalar product matrix. So the final solution will look like minus 2 times x y plus x squared sum over the plus dimension reshaped to this shape. Minus 1 means that the size of this dimension will be computed automatically based on the size of the original array. And the same thing for y. Well,
There is a type shape mismatch. You should have y transpose in matrix multiplication.
oh yeah, I see it. Same here. So now we have the matrix of distances, and we can check that we obtain the same answers. Okay, I believe that was more or less clear. So, interesting part now. How to do the GPU computations. Well, it is quite easy. We use actually three tensor methods for it. The first method is CUDA, which takes optional ID of the ID of the GPU you want to store your data on. CPU, which returns your tensor back to RAM, and the method 2, which can which returns the input tensor, which returns self if the specified device is the same as the tensor device, or it returns the copy of the tensor on the specified device if this device is different from the original tensor device. The main point is that you to make an operations, some mathematical operations over two tensor, they have to be on the same device, or both on the CPU, so in RAM, or both in the GPU memory of the same GPU, and you have to ensure that it happens. So if we, for example, I don't know, let's compute this one on the GPU. Well, this one. If we have our tensor x on CUDA, and we try to multiply it by the tensor not on GPU, we will have error. But if we place both tensors on the GPU, we obtain some result. And well, here is the result. Just a tensor. And well, if you print this tensor without transferring it to CPU, well, you will see that the tensor is stored on CUDA, actually. Stored on GPU. And well, I want to stress out again that these operations does not affect original tensor. So if we check what is white now, for example, it is stored on the CPU. Well, and one more point is the environment variable CUDA visible devices. So you just write something like equals to 1, or well, using this environment variable, you can remap the IDs of your system GPUs and the IDs of GPUs you use inside your program. So if you write well, something like that, then inside train PI, when you call CUDA without arguments or CUDA with zero ID, you will actually get into the first system GPU. Okay, that's all I have to say about it. Any questions? Okay. Now, the second interesting part about each dependent library is automatic differentiation. How it is implemented in PyTorch. The point is that in order to give a computation graph, we have to create a tensor before doing mathematical operations. We have to show that the tensor requires gradients, so we need to backpropagate to it. And when PyTorch sees that the tensor requires gradient, it begins to store the intermediate results which we need to do backpropagation. So we create such a tensor. We then we apply some function to it, do some mathematical operations, and so on. Then we have a scalar. We take backward of it, and the gradient will be available in the grad field of the original tensor. And the same thing works for several tensors. So we can say A is a tensor which requires gradient, B is tensor which requires gradient, and so on. Then we have function of all these tensors, and we once again backpropagate through them. Well, yes, if we take a function, well, if we want to propagate from something and it have no computational graph, so to compute it, we didn't use any tensor which requires graph, you naturally get error. Once again, documentation official, you're welcome to use it. Well, actually, it seems more or less natural now, but the first different libraries used a different approach. That approach was called static computational graph, while PyTorch uses dynamic computational graph. So why dynamic? Because you build your computational graph through which you do backpropagation. When you, in the process of the computing the forward pass. For example, such libraries as Tianad or TensorFlow of the first version, or Caffe, they just first you define your neural network, which means that you define your computational graph. Then it, well, let's say compiles, actually turns into some executable code. For Siana, for example, you can see a lot of intermediate C files in the process of compilation of the model. In TensorFlow, it just turns into some inner representation. But the point is that once you define the computational graph, it is fixed. You just well feed different input tensors to it. The pros of static computational graph is that once it is fixed, you can optimize it and compute everything more efficiently. But actually, in practice, we see that training in PyTorch and TensorFlow works in a similar time. So we have not big overhead for the computation graph. But now TensorFlow supports the dynamical computational graph as well in its second version, and PyTorch allows to export its models into static computational graphs, which are more suitable for production, for example, in Torch script. So once again, let's not dive deep into this topic, but you have documents once again. Okay, let's consider example. Here we have two different tensors which requires gradient. We compute the third vector, we turn it into some scalar, and we call the backpropagation from this computational graph. And naturally, we see that the gradient with respect to each component of the first tensor is just the value of the second of the same component of the second tensor, and vice versa, which is the correct answer. So this is how it works. Now detection variables. Actually, what does detach? It just interrupts or breaks your computational graph. So actually, it returns a copy of tensor, and the backpropagation doesn't go through this copy operation. Why do you need detection? Well, the most common error which I see in training loop in deep learning was not detaching loss variables. So imagine that you have your training loop and you want to compute some running average during your training loop to print on the screen or to, well, I don't know. This is just nice. And you compute your loss function, and then you backpropagate through it, and then you add your loss function into well to the to your average. If you do so, your average will be not just a number; it will be very large computational graph, which includes all loss computation which you had in your training loop. So you will get out of memory error very soon, or not very soon if you are not so lucky, but you will get it anyway. So to avoid such an error, you can well, you have to detach your losses before average them. That's it. But actually, you can use it in your model as stop gradient. This is quite popular too. And there is in place version of detach, but I've not seen it used a lot. So here is the example. We have one tensor which requires that. We have another tensor which requires that. But we detach it and we once again compute the same expression over these two tensors. But now the first gradient is gradient and the second gradient is known because we detached the original tensor from the compression graph. Now the important part. When you call backward 2 times, the gradient in the tensors are not overwritten, they just added to each other. So why do we need it? For example, you can artificially make a larger batches for your optimization. You can compute well, if, for example, the maximum batch size you can store, you can compute on GPU is 16, and you want your batch size to be 256 due to optimization well, reasons of the problem. You can just take 16 batches, uh, uh, 16 objects each. Then 16 times you do compute loss and do backpropagation. And after that, the gradient variable will store the gradient for the tensor will be the gradient for the virtual batch of size 256, for example. And here we have the example of such behavior. We compute the gradient for x squared, where x is the tensor filled with ones. Actually, it is just two. Well, a tensor filled with twos. And the gradient for 1 or x is minus 1. But when we compute it and call backward, we get the grad equals to 1. So if you don't want such behavior, you have to manually fill with zeros your gradients between do backward passes. So here we do backpropagation and print gradient, then fill the gradient with zeros, and after that do backpropagation again and get the correct answer. Okay. This is it. Now, actually, the computational graph is array. So it have leaf. Well, okay. Maybe not exactly a tree, but anyway, there is so-called leaf variables. Well, actually, the leaf variables are just well, input tensors the tensors which were not the original tensors which requires graph, from which we start to build this computational graph. That's it. So when we call backward pass, the gradients are stored only in such leaf variables, leaf tensors. So x is a leaf tensor, y is not a leaf tensor because it is a result of mathematical operation. And p scalar is not a leaf, once again. So that's what we see. Here is another example. We have two leaf variables. We have the two intermediate not leaf variables, and we see that not leaf variables have no gradients, and also each tensor have this leaf flag, which is true for leaves and false for not leaves. Okay. What if we need, for some reasons, to compute gradients for not leaf variables? For example, we need not only gradient with respect to x and y, but we need a gradient with respect to intermediate variable z as well. We can use the method retain grad for this intermediate result, but we need to call it before do backpropagation naturally, because otherwise, well, all intermediate results will be lost, and we will not be able to restore the actual value of the gradient. So here we have not leaf. We do some operations over it. We obtain our scalar, and then we call backpropagation. Well, the point is that if you well, if you have no leaf variables, so actually all of your well, if all of your tensors doesn't require graph, and then you take some intermediate result and try to obtain graph from it, you will not be able to backpropagate to it because the computation graph was not built. So here we have the error. Okay. Well, but if we say that x requires grad is true here, it will work. Okay. Any questions so far? Okay, now we have the second problem. We want to do some optimization. The point is, well, the problem is follows. We have a set of points in 10-dimensional space. And we want to build a linear transformation of these points into two-dimensional space. So we just multiply them by some matrix and add bias. And we want that transformed points wise, we want them to lie around the circle with radius 1. So, well, we want to have a linear transformation which transforms points from 10-dimensional space into something like this figure. How do we do that? Uh, we just define a loss function which encourages our mm, mm, transform points to lie near this circle. And then we solve the optimization problem with respect to the parameters of linear transformation. So the point is that once we have automatic differentiation, we can how to say use something like declarative way to define the properties of our model. So we just construct a loss function which says which model is good and which is bad, and then everything such as optimization and so on will be done for us by the library. So which function you propose here is follows. Firstly, we compute the norm of the transform point, which Euclidean norm. Then we compute the distance of this norm to the one to the identity circle. We compute well L1 and L2 distances and take the weighted average. And this is the first part of the loss. Unfortunately, it is not enough because we can just map all the points into the same point, just to have zero matrix and identity bias. And therefore, all of the points will lie in the distance 1 from 0, but they will not be placed on the circle, and that is not a solution which we want. So we take the second part, which penalize the proximity of the mapping to the bias, well, to the central of this mapping. So first of all, we want this penalty to be 0 when the distance from the bias is larger than 1. Secondly, the closer the mapping to the bias, the larger is the penalty. So as we see, if this distance is 0, then this penalty is infinity, and if this distance is 1, then this penalty is comes to 0. So we have our loss function. You have to implement it, and this is how the original transformation works. Here it is. And after defining function, you have to write some optimization to obtain good linear transformation. once again, you have your time. And if you have questions with respect to the statement or the solution, you are welcome. Any luck? Okay, let's get to it. So first of all, we compute our transform points. That's it. Now we compute their distance to 0. Well, quite simple as well. Also, we compute their distance to the bias. We will need it into the second loss, so y minus now we have f0 as that's it, and f1 equals to 1 over yb minus 1, and well, clump for PyTorch is the same as clip for NumPy. So we just say that if something is lesser than 0, it will be 0. And then we return f0 plus f1 averaged. Okay, it works. Now, to the optimization part. What do we have? First of all, we need to say that our parameters require that. Second of all, train loop. Loss equals to f of wb. Well, one more check. Back over here. Well, it doesn't work because we have not enabled gradients, but now gradients are working. Why did I do that? Because originally gradients for W and B was none, and now it is the same value, so I can write this thing. And now the problem is that if I write this code. Mm, for example, it contains an error. What is the error? Yeah, exactly. The problem is that since the W requires graph, we just continue to build our computation graph with this through this gradient step. So how can we handle it? The first way is to use this data field, which just well shows stores what's inside this tensor, and well, if you write such code, we will not build further computation graph. So let's check it out. Okay, once again, here we need DFH. Well, not so good, but we have not so many iterations now. More, well, elegant way to solve the problem is using no grad context. What is that? It is just well, probably you know what is context in Python. Well, even if you don't know, the point is that inside such construction, no computational graph is built. So you say to PyTorch that we don't need gradients inside this. So once again, we can and where is the gradient? Okay. That's right. What happened? Oh, I see. So, well, if we run it for a long time, you will get something like this. So, well, for me, it is interesting that we have such a linear transformation which maps normally distributed points in 10-dimensional space to 2-dimensional circle. But the point is that this is well, is how can we implement optimization in PyTorch? Well, naturally, nobody does that because we have optimizers in torch.optim module and we used them in the previous seminar, and that's how we need to do it. So now I think we have no time to do the rest of the notebook, so I'll just give you a brief about what happens there, and you can do it in your free time if you want to. So what do you have here? Mm, we want to write our own neural network. Ye- and to solve some classification problem, it is digits classification problem here. Mm, hmm. Uh, we do well. We turn the numpy arrays into torch tensors. We do some normalization over them. Um, the point is that to understand the PyTorch model structure, you can implement the similar structure by yourself. So mm, what methods are necessary in such structure? Firstly, it has to maintain the list of its children. Uh, so each neural network must maintain the list of its layers. Secondly, there must be a recursive function which returns the list of parameters of the neural network. Um, well, and there are some functions which turn the neural network from train to test evaluation mode. Well, what does it mean? It means multiplication by the constant instead of sampling for dropout, as you were told on the lecture, or it means using running averages instead of actual mean and average in batch norm, and so on. So now, once we have this original model class, you can inherit different layers from this model, and mm, here we just re-implement parameters function. But in PyTorch, we define our parameters with neural network parameter wrapper. So, well, if you have some weight W inside your PyTorch neural network, which requires graph, you have to wrap it into such wrapper, which tells PyTorch that this that this tensor is a parameter and nothing else. So, and each layer have it forward function, actually, which is called when you just call your model. Um, here is different layers, and here is the layer which defines network, which contains a sequence of different layers. And here is a loss function, and here you can implement different optimizers. So just stochastically descent, and well, after that, stochastic gradient descent with momentum, and Hermes prop and Adam. Not so hard, actually. And here is example of train loop mm, with rain average, for example. And for those who, well, uh, mm, mm, more interesting, we have mm, dense layer with dropout. So here we can use the benefits from the dynamical computational graphs, which so the point is that if we have dropout, we zero some activations, and actually we have no point in multiply them by the next linear layer, because we just multiply zeros. So we can avoid such computations and probably speed up our program. So here you can implement dense layer with dropout, which well sees which columns of the input data are zeros, and then select only non-zero columns from the input activations, and then do reduced well the matrix multiplication with the reduced input size. And actually, when you done it, you will find that you can observe some speed up only um, for very wide layers and for very high dropout rates. So it is not practical at all, but probably it is interesting as well. So probably we are out of time. Do you have any questions regarding the seminar? Okay, so thank you for your attention and have a nice day.